So in case number 13, we are going to talk about how glucose is, the level of glucose is maintained in our system, mostly in the blood system. So let's look at page 3. Start from part 1. You should know that type 1 diabetes is caused by the fact that insulin is not produced. So here comes the enzyme that plays an important role in maintaining glucose concentration in our blood. Two enzymes actually. So let's look at the picture on page 3. One of those enzymes is insulin. So everyone knows that insulin is super important, and if we don't have enough insulin, we are not going to maintain our blood sugar level at the correct position. So that means the patient will have diabetes. The other one is glucagon. So those two enzymes actually function two different reactions. Insulin change glucose to glycogen. Glucagon change glycogen to glucose. And this happens in liver. As we talked about before, liver is a very busy organ, and this is one of the important functions that liver do. Okay, so let's see. For example, this morning I had a muffin, and I have a high blood sugar level now. And what should I do? There are so many glucose molecules in my blood, but I cannot use them all. And this is a high glucose level case. At this situation, I'm going to produce insulin. And insulin will tell the system to change the glucose in my blood into glycogen. As we know that glycogen is used to store glucose. Okay, and you still know what glycogen looks like, right? It is a branched molecule made up with D-glucose. So insulin will collect those glucose in my blood and then change them into glycogen and store them in the liver as well as in muscle. Okay, but we only talk about the liver here. Therefore, my glucose level will decrease. Okay, so let's think about the other situation. For example, I didn't eat for a whole day. Okay, I'm very hungry, and my blood glucose level is very low. So what should I do? I'm going to activate glucagon. Okay, glucagon, the enzyme on the right. And what glucagon do is that they will change glycogen into glucose. So glucagon will tell liver to release glucose from glycogen, and therefore my glucose level will go up. Okay, so those two enzymes, they have different functions, and they are regulated by the level of glucose in our blood. Okay. Alright, so after we talk about this figure and we know the important function of those two enzymes, we can look at those questions. Question number 11. In type 1 diabetes patients, the cells are starved when insulin is not present. What does this mean? What does the cell are starved? Can they get glucose? No, they can't. Glucose cannot be recruited and stored as glycogen. So where are those glucose? Where do those glucose go? They are dissipated from our system. Okay, they are released from our body. Okay, this is why we call it, diabetes. So insulin is not functioning here. We don't have enough insulin to store glucose into glycogen. Therefore, our cells are starved. Question number 12. The liver controls fuel metabolism in the body and maintains a glycogen store for maintaining blood sugar levels between meals, okay, which is super important. We want to keep the blood glucose level constant. For type 1 diabetes patients, how much glycogen is the liver able to store? For the diabetes patient, how much glycogen is the liver able to store? Will it be the same as a normal person? No, it will not be same because in those patients cannot produce enough insulin. So not enough due to lack of insulin. They won't have enough glycogen. And that's a problem. That will be a problem. Okay. So next question, in type 1 diabetes, a decrease in the intracellular concentration of glucose acts as a signal that triggers the release of glucagon from the pancreas. Okay, what effect will an increase in the concentration of glucagon will have on the concentration of glucose? Alright. Again, decrease of glucose level will activate glucagon. And what is the function of glucagon? Let's look at the picture. It will release glucose. It will release glucose. Okay. Alright. So that means the level of glucose will increase. But what about fatty acids? What about free fatty acids? So we have talked about one molecule that used to store fatty acids. Do you still know what it is? It starts with T, TAG. Alright, so fatty acids are stored as TAG, triglycerides. And when we feel starved, when we have a low concentration of glucose, TAG will also release fatty acids because we can use fatty acids to generate energy molecule, which is ATP. Okay, so fatty acids will also be released by glucagon. So both of them will increase. We are going to increase the concentration of glucose. We are going to increase the free fatty acids in the blood so that we can get enough energy. Alright, so next question. Why do cells metabolize more fat in type 1 diabetes? Again, it's about the function of insulin. What does insulin do? Insulin tells the body to store fat and burn glycogen, to store fat and store glycogen. So when I have a high level of glucose in my blood, that means I want to store those glucose. That means I don't want to release fatty acids. I want to store fatty acids. Okay? But what about type 1 diabetes patients? They don't have enough insulin. That means I cannot store fatty acids. That means I cannot store glucose into glycogen. Alright, so insulin tells the body to store fat into TAG and burn glucose and glycogen. If we don't have enough insulin, fat will be released and metabolized. If we don't have enough insulin, fat will be released. Okay. And this is actually a natural reaction of our system to starvation. If we feel hungry, we are going to burn fat. Alright, so next question, 15. This patient was given insulin as part of a treatment. This is what we normally do, okay? So what effect will this have on A, blood sugar concentration? So what if we give the patient insulin? Insulin will tell the system to store glucose into glycogen. So what do you know about blood sugar concentration? It will decrease because all those glucose they are stored as glycogen. Okay. What about rate of glycolysis in cells? What about the rate of glycolysis in cells? Again, insulin tells the body to burn glucose. When we produce insulin, it means that we are going to generate some energy. So the rate of glycolysis in cells will increase. We are going to burn glucose. C, rate of fatty acids catabolism. So that is the release of fatty acids. Again, insulin will tell the body to store fat. So fatty acids catabolism will be decreased. We are going to store the fat, and we are not going to, break down fat. Catabolism, again, it means break down molecules. So we are not going to break down fatty acids, but store them. So fatty acid catabolism will decrease. Alright, so again, when you have any questions, please write it down and send it to my email. Okay. Let's look at part 2. We're going to talk about gluconeogenesis, beta oxidation, and ketone body metabolism. First, what is gluconeogenesis? We are actually going to answer that question in question number 17. Okay. So, but let's look at this picture on page 4. Let's look at this picture, picture 2. You still remember? Well, actually, I showed this picture before to you, right? You still remember the process, the pathway from glucose to pyruvate, right? This is called glycolysis. This is the first step, the first pathway that we metabolize glucose, okay, to get energy from glucose. And then pyruvate will become acetyl-CoA, and then acetyl-CoA will go into a second pathway, which is called TCA cycle. So acetyl-CoA will go to this TCA cycle, and both of those two carbons in acetyl-CoA will become carbon dioxide, and the energy will be released and stored in ATP. Okay, but there is another way that we can generate acetyl-CoA besides glucose, and the other way is from fatty acids. Again, we release fatty acids from TAG, triglycerides, and then fatty acids will become fatty acyl-CoA, and this is called beta oxidation. So fatty acids becomes fatty acyl-CoA is called beta oxidation. And then it will become acetyl-CoA, and then go into TCA cycle to generate energy. Okay, and if acetyl-CoA is not going into TCA cycle, it will become acetyl-CoA. It will become acetyl-acyl-CoA and acetyl-acetate, acetone, and the other molecule. So acetone and beta hydroxybutyrate, they are ketone bodies. Alright, so this picture actually includes all those three important things that we are going to talk about in part 2. Oh, it doesn't include gluconeogenesis. So gluconeogenesis is the reverse process of metabolism of glucose. So that is the regenerate of glucose. So again, we're going to talk about that in question number 17. So look at question number 16. What pathway does the liver normally run to provide glucose to the rest of the body? How would the liver produce glucose? Again, from glycogen. So the liver releases glucose from glycogen, and this process is called glycogenolysis. Okay, this is glycogen lysis. So you can think about this word as two parts: glycogen lysis, and we know that lysis means break apart. So we are going to break down glycogen to make glucose. And this word is different as the next word. gluconeogenesis. Okay, question number 17. Does gluconeogenesis help the starved cells in the body for the patient with type 1 diabetes? So again, what is gluconeogenesis? It is the regenerate of glucose. So make glucose from non-carbohydrate sources. Make glucose from non-carbohydrate sources. This is gluconeogenesis. We are going to regenerate glucose. And will this help starved cells? Yes, it will. Those newly made glucose will be released back into the blood system and raise blood glucose level. So gluconeogenesis is one way to fight the low level of glucose in our system for type 1 diabetes patients. This is, again, a natural response of the system. So 18, what metabolic pathway catalyzes free fatty acids into acetyl-CoA? Beta oxidation. Okay, so from free fatty acids into acetyl-CoA, this is beta oxidation. Fatty acids will lose 2 carbon each time. This is why we call it beta oxidation. Okay, it happens at the beta carbon. Therefore, we lose 2 carbon. Fatty acids will lose 2 carbon each time. And again, fatty acids has a lot of energy in it, and normally we don't use it because we have glucose, and glucose is our preferred molecule to generate energy. But what if we don't have enough glucose? We are going to burn fatty acids. And how do we do that? We are going to use beta oxidation and to generate acetyl-CoA, and therefore acetyl-CoA will go into TCA cycle to generate energy molecule ATP. Okay. So 19, draw out the reactants and products for beta oxidation of the C60 saturated fatty acids. What is C60? What does 6 mean? 6 means that this fatty acid has 6 carbon. 6 carbon. What about a 0? 0 means it doesn't have any double bonds. It doesn't have any double bonds. Okay. Therefore, it is saturated fatty acids, right? Okay, so how do we write this reaction? It looks like this. Again, 6 carbon. 6 carbon. So count all those carbons. 1, 4, that's 5, and then 1 carbon is in C double bonded O, is in carboxylic acid. So totally 6 carbon here. It's linked with CoA, and then we need help of 2 cofactors. One is FAD, the other one is NAD+, as well as water. And then we are going to generate how many acetyl-CoA? 3 acetyl-CoA, because each acetyl-CoA contains 2 carbon. Each acetyl-CoA contains 2 carbon, so 3 acetyl-CoA. Totally we have 6 carbon. And again, this fatty acid has 6 carbon. FAD will become FADH2, NAD plus will become NADH. So what is the function of NADH2 and FADH2 and NADH again? Their function is to carry electrons and H+. Okay, their function is to carry electrons and H+. Alright, so next question, 20. Can the liver share the acetyl-CoA product with other cells in the body, like it does with glucose? So the liver can share glucose with other cells in the body by releasing glucose into blood, right? Through gluconeogenesis. When gluconeogenesis also happens in liver, and when glucose is regenerated from liver, it will be released in blood. Okay. But how about acetyl-CoA? Can we release acetyl-CoA for other cells? Actually, we cannot. This actually comes back to the whole process, and we would like to we need to know that this whole process, the TCA cycle as well as beta oxidation, acetyl-CoA, they all happens within mitochondria. So mitochondria is called the powerhouse of our body, right? So mitochondria is where ATP is generated, and it's also where TCA cycle happens. And acetyl-CoA is generated within mitochondria. And as we know that mitochondria has two membranes, the inner membrane and outside membrane. Can acetyl-CoA go across mitochondrial membrane? No, it can't. No, it can't. Why is that? Because CoA, what is CoA? CoA is coenzyme A. Okay, coenzyme, as you can see, is a pretty big molecule. So when acetyl, those two carbon is linked with coenzyme A, it's linked with a very big molecule, and therefore it cannot be transported out of the membrane. So acetyl-CoA cannot go across mitochondrial membrane because there is no transporter for that, and it's too big. Next question, 21. Given that the liver controls fuel metabolism for the entire body, how can it share these acetyl-CoA molecules with other cells in the body? We do want to do that, right? So acetyl-CoA cannot be directly transported out of the mitochondrial membrane. So how do we transport those energy, share those energy with other molecules? We do it in the next step, in the second molecule within the TCA cycle, which is citrate. Okay, so acetyl-CoA will join OAA. If you still remember this, so we talked about this last case in TCA cycle. So acetyl-CoA has 2 carbon, OAA has 4 carbon, so 2 carbon joins 4 carbon becomes 6 carbon molecule, that is citrate. This is why it's also called citric acid cycle. So after it becomes citrate, there will be a transporter to transport citrate out of mitochondria. So acetyl-CoA can be moved out of the mitochondria after it becomes citrate. That's pretty smart, right? So we do need a transporter to change citrate out, but we don't want to transport acetyl-CoA out because that's pretty important for us to generate energy. 22. How do the patient's values for each of the following look upon admission to the hospital? Oh, you can find it in page 1, right? So I will directly give you answer here. Blood glucose level, which is high, ketone body concentration high, blood pH, which is low. The patient has a low pH. Why is that? Why does the patient has a low pH? Low blood pH. Let's look at question number 33. Okay. So what functional group present on most ketone bodies can affect blood pH? So I have listed 3 ketone bodies here for you. One is acetone, the other one is acetate, and the last one is 2-hydroxybutyric acid. Okay. So what functional group in those 3 ketone bodies can affect blood pH? Can you find it? Yep, it is carboxylic acid, COOH. Alright. So how will this functional group affect blood pH at physiological pH? Will it increase the blood pH or decrease blood pH? It is an acid, so it will decrease blood pH. Okay, carboxylic acid will decrease blood pH. What functional group can you find in acetyl, the first ketone body? Does it have carboxylic acid? Look at the first one, acetone. No, it doesn't have a carboxylic acid. So what functional group is that? That is ketone. That is ketone. C double bonded O, C. Okay. Alright, so next question. 24. What is the reason for the patient's strange smelling breath upon presentation? Okay, what is that? What caused that strange smelling breath? The ketone. Okay, the ketone bodies. They have a very interesting smell. Okay, turn the page. Question number 25. Why is bicarbonate decreasing while the amount of ketone bodies is increasing? Oh, let's think about this. This is actually involved the blood pH system. Okay, we are going to work on the blood pH buffering system again. Okay, so let's see. I probably want to give you a few seconds to write down the blood buffering system. Okay, one of the questions later we'll need it. Can you do that? So, blood buffering system. We start with COO, CO2, okay, carbon dioxide. With water, it becomes H2CO3. And then carbonic acid will dissociate into H plus and bicarbonate. Okay, so let's look at this blood buffering system. Why is bicarbonate decreasing? So first, ketone body is increasing. When we increase ketone body, we are increasing the amount of carboxylic acid. So when we have a lot of acid in our blood, again, pH will decrease. So when pH decrease, that means we have a lot of H plus in our system, right? So look at this blood buffering system. When we have a lot of H plus, where the reaction goes, to the left or to the right? When the H plus increase, it will go to the left. The whole system moves to the left. Therefore, the concentration of bicarbonate will decrease. Okay, ketone body increase, therefore H plus increase, so the whole system shift to left, and bicarbonate level will decrease. Okay. So next, predict how blood pH would change if bicarbonate disappeared completely from the patient's blood during acidosis. Alright, what do you think? So when we don't have bicarbonate in our system, when we don't have bicarbonate, which is on the right, when bicarbonate level is low, the whole system shifts to the right, therefore generating a lot of H plus. When we have a lot of H plus, what do we know about pH? pH decrease. Okay, that will cause acidosis. So 27, summarize how increased synthesis of ketone bodies leads to metabolic acidosis. What do you know? Ketone body provides H plus, therefore decreasing, and it will decrease bicarbonate level. And when we don't have bicarbonate, it will make it worse. That will cause acidosis. Okay. 28. Summarize why the patient unable to maintain blood pH at normal levels despite the buffering system present in the blood. So we do have buffering system, but the patient cannot maintain blood pH. Why is that? Because we don't have enough bicarbonate. Alright, we don't have enough bicarbonate in our system, so the buffering system will not work without bicarbonate. 29. Why was the patient given an infusion of bicarbonate? Why is that? The reason is pretty clear now, right? To restore the buffering system, right? So we do need bicarbonate. We increase bicarbonate level, it shifts to right, H plus decrease, and more importantly, when we have bicarbonate, we can have a buffering system. So we need to restore buffering system. Okay, so that is part 2. Part 3 will mainly about blood pH and respiration rates, which we have already talked about in one of the previous cases. Okay, so we are going to review all those questions again. Question number 30. What is patient's respiration rate at presentation, and how does it compare to the normal rate? Respiration rate is high. Okay, it's higher than normal. What do you know? How do you call that? When the patient has a respiration rate higher than normal, we call it hyperventilation. That we call hyperventilation, right? So 31. What is happening to the partial pressure of CO2 in the blood during the Kussmaul respirations, and why is the patient's PCO2 low upon admission to the hospital? Okay, let's think about first, what is Kussmaul respiration? So Kussmaul breathing is a type of hyperventilation. It is a deep, labored breathing rate with a deep, labored breathing rate. Okay, so when the patient has a hyperventilation, that means the patient breathes very quickly. So what do you know about CO2 level? CO2 level will decrease. CO2 level will decrease to the normal CO2 as in the air, right? So why is the patient's PCO2 low upon admission to the hospital? Because of hyperventilation. Okay. Alright, so next question. Write the blood buffering equation below. Okay, I believe you can do that. Alright, so write the blood buffering equation here. Let's answer the questions now. If excess CO2, a lot of CO2 is exhaled from the lungs, if we release a lot of CO2 from our system, what happens to each of the following? So what do you know about PCO2? We release PCO2 from our system, so PCO2 will decrease. Okay, when we have a low concentration of CO2, where the reaction goes, where the buffering system goes? To the left. Okay, it goes to the left. So what do you know about bicarbonate level on the right? Bicarbonate will decrease. Okay, how about hydronium, which is H+? H+ will also decrease. Okay, so when we have decreased when we have a decreased H+, what do you know about pH? pH will increase. And when the patient have acidosis, and the patient does want to have an increased pH, right? Increased pH will help a patient with acidosis. So how does acidosis affect respiration rate? This is again a natural response of our system. When we have acidosis, that means we have a low blood pH, and we do want to increase our blood pH. How do we increase our blood pH? By decreasing PCO2, by decreasing the level of CO2. How do we decrease the level of CO2? Increase respiration rate. Okay, by increasing respiration rate. So how does acidosis affect the respiration rate? It will increase respiration rate. Again, this is the natural response of our system. Okay, so we are done with this case now, and we have one more case to go. Alright, see you guys.